Okay. It'll look a little bit different if the matrix has more columns than rows. So I want to put something like this into row echelon form. Well, it winds up being relatively simple. So I need to have ones on my main diagonal entries, which are here and here, and zeros below that. Okay? So I need to make this 4 into a 0, so I can take 4 times row 1 minus 3 times row 2. I need to make this into a 0, so I can take row 1 minus row 3. I need to make this into a 0, so I can take 5 times row 1 minus row 4. Let's see what that gets us. Row 1 stays the same. 4 times row 1 minus 3 times row 2, that's 12 minus 12. That's 0. And this is 8 minus 21, it's negative 13. Row 1 minus row 3, 3 minus 3 is 0, 2 minus 8 is negative 6. 5 times row 1 minus 3 times row 4, that's 15 minus 15, which is 0. That's 10 minus 12, which is negative 2. Alright, now in this case, 13 and 6 and 13 and 2 don't go very well together. So in this case, I'm going to make my 1s on the diagonal right now. I need to do that. I need to take row 1 divided by 3. I need to take row 2 divided by negative 13. Alright, so that gives me 1, 2/3, 0, 1, 0, negative 6, 0, negative 2. Alright, but now I need to have zeros below the diagonal. So I want to turn these into zeros, and I can do that by taking 6 times row 2 plus row 3, and 2 times row 2 plus row 4. We got 1, 2/3, 0, 1, 0, and then 6 plus negative 6 is 0, 2 plus negative 2 is 0. And so we wind up with this, and this is our matrix in row echelon. I mentioned toward the beginning that we're doing this and we can represent our systems of equations as matrices. So let's say we had the system x minus 3y plus z equals negative 1, 2x minus y minus 2z equals 4, and negative 3x plus 2y plus 2z equals negative 6. Right? If we were going to solve this as is, we might take 2 times this equation and subtract this equation to get rid of x. Then we might take 3 times this equation and add it to the third equation to get rid of the x there. And then use these two equations to eliminate y here, and then back substitute to solve for x, y, and z. Okay? We can do that whole process as a matrix. And I think doing it as a matrix, it's the same process, but I think it's a lot cleaner when you represent the system as a matrix. And you can do that just by putting the coefficients on your variables as the entries in your matrix. We've got here a 1x minus 3y plus z. We've got a 2x minus 1y minus 2z. And we have a minus 3x plus 2y plus 2z. Okay? And then, so these are your coefficients. Okay? And then your solutions, your answers, are going to be sort of part of the same matrix. We're going to make what's called an augmented matrix. Meaning that we have, this will be our coefficient matrix, and then we're going to have our answer matrix, but we're going to kind of smush them together into one matrix. And to indicate that it is an augmented matrix, and that one side is our coefficients, one side is our answers, we're going to put colons in between. Now when we do our operations, we're really just going to be dealing with a 3 by 4 matrix. But the colons just remind us that this is representing a system, and that they kind of stand in place of the equal sign that we have when we're dealing with our equations. Okay. So from here we can go ahead and do our Gaussian elimination. In order to cancel out this 2, we would go ahead and take 2 times row 1 minus row 2. To get rid of this 3, you could go ahead and take 3 times row 1 plus row 3. And what does that give us? Well, row 1 stays the same. Alright. And then 2 times 1 minus 2 is 0. 2 times negative 3 is negative 6. Minus negative 1 is negative 5. 2 times 1 is 2. Minus negative 2 is 4. I keep that colon there. 2 times negative 1 is negative 2. Minus 4 is negative 6. And down in my third row, 3 times 1 plus negative 3, 0. 3 times negative 3 is negative 9. Plus 2 is negative 7. 3 times 1 is 3, plus 2 is 5. 3 times negative 1 is negative 3, plus negative 6 is negative 9. All right. The next step in our Gaussian elimination is to get rid of this other entry below the diagonal. So we're going to want 1s on the diagonal, and we're going to want, zeros below the diagonal. And to do that, we can take 7 times row 2 minus 5 times row 3, which may not be the nicest numbers to work with, but we'll get through it. First row stays the same. Second row stays the same. And the third row, 7 times 0 minus 5 times 0 is just 0. That's negative 35 plus 35, also 0. And then we have 28 minus 25, which is 3. This is negative 42 minus negative 45, so that's negative 42 plus 45, which is also 3. Then our next step is to make 1s on the diagonal. So we take row 2 divided by negative 5 and row 3 divided by 3, which leaves us with 1, negative 3. Our first row stays the same. Then we have 0, 1, minus 4/5, 6/5, 0, 0, 1, 1. And at this point, we remember that this was representing a system. So since our last equation is reduced to 1 and 1, this column, remember, was the coefficients on z. This column is the coefficients on y, this column is the coefficients on x, and these were our answers. So what this represents here is z equals 1. So we have z equals 1. What this represents is y minus 4/5 times z, which is 1, so that stays 4/5, equals 6/5. So we can add the 4/5 over and get that y equals 10/5, which is just 2. And what this represents is x minus 3y, y is 2, plus 1z, z is 1, equals negative 1. So we can work this out. That's 1, negative 6, plus 1 is negative 5. We add the negative 5 over and get x equals 4. And so we have our solution to the system of equations. That is 4, 2, 1. Now,